Hey class, I wanted to pop in and much like I did for section 10.2, I wanted to work on some of these problems from the homework in WebAssign for section 10.3, where we were learning about parametric equations and calculus. Okay, so let's do some select problems here just to give you a few supplemental problems, some examples that you can work through that might help you as you work on your own homework. Okay. So for this first question, it's asking us to find dy dx. So if we recall dy dx, which is the derivative of y with respect to x, is given by this formula by theorem 10.7, which says we need to find dy dt and then divide that by dx dt. Okay. So we have to find those two derivatives as we sort of work through this problem. And I like to start with the numerator first just to make things a little bit easier, just to keep some organization for this. So we're going to focus on the first equation, this parametric equation we have for y. Y is equal to 7 minus 2t. So that means y prime with respect to t is just going to be 0. Uh, and then minus 2. So we should just have a negative 2 for our numerator there. For the denominator, we're going to be looking at x prime. So taking the derivative of x with respect to t tells us to go ahead and look at this other parametric equation, x is equal to t squared. And if we take that derivative with respect to t, we just get 2t. So that's going to be our denominator. Once we have that, with a little bit of simplification, we can see that the 2's will cancel out. So we should have negative 1 over t, which is the function that represents the derivative of this curve. So dy dx is just going to be negative 1 over t. Negative 1 over t. We can go ahead and type that in and submit our answer. And we should get some green check marks, feel good about ourselves, and then maybe spend the rest of our lives chasing that feeling. Okay. So let me go ahead and clear my drawings. If you kind of systematically go through these problems, they should be pretty straightforward in that regard. So I'm going to skip to question number 3 because that's going to level us up from just thinking about the first derivative, dy dx, to the second derivative. Okay. So in other contexts, you might hear the first derivative be asked of you to find the slope of the curve, and they might say the slope of the curve at a particular point. So just watch out for that. And then the second derivative sometimes might be branded as find the concavity of the curve at a particular point. So for this next question, we're going to have to do just that, find the first and second derivative. So let's read the question. Question 3 says, find dy dx and d squared y over dx squared. That's our second derivative. And find the slope and concavity, if possible, at the given parameter value. Okay. So they've given us this parameter value t equals 4 that we need to be mindful of. But as far as, the process of getting through this problem, I would say let's just start with the basics. Let's find dy dx, the first derivative. And using that formula that we used just moments ago, remind ourselves that that's going to be the same thing as dy dt, okay, over dx dt. Okay. So we'll sort of use two different colors to kind of code what we're looking for here. We're going to start off with y, which is 5t minus 8. So that means that y prime, remember we're taking the derivative with respect to t, is just going to end up being 5. And then the minus 8, if we take the derivative of that, is just 0. So the numerator is just going to be a 5. Okay. The denominator here is going to be the derivative of the function describing the x coordinates here, and that's just 6t. So taking the derivative of that x prime is just going to be 6. Okay, so we have 5 over 6, and that does not seem to be a function of t at all. It seems to be a constant value. So let's go ahead and type that in just so we don't have to worry about it. 5 over 6. Okay. And that means that, if we were asked to evaluate this at uh, at t equals 4, that means that there is not a t that we can plug in there. So that's just going to be a constant value of 5 over 6. So it has a constant slope for this function. So that should just go down here for slope, 5 over 6. There was nothing to plug in. Okay. So now let's turn our attention to the second derivative. Okay, so let me get my markers here. If we are looking for the second derivative, written as d squared y over dx squared, notationally it's kind of convoluted. Remember that we can reapply theorem 10.7, which says we already have our dy dx. So what we really just need to do is take the derivative with respect to t of the first derivative that we just found in the previous problem. So we can write that as dy dx here. And then the denominator is going to remain that dx dt. Okay. So if we want to clarify this, because like I said, the notation becomes kind of cumbersome, what we're doing is taking for the numerator the derivative with respect to t of that derivative we just found, that 5 over 6. Okay, so we'll just put 5 over 6 here, which is a constant, and then divide that by the same denominator that we had in the previous problem, which is just x prime, right? So that's just going to be a 6. But the nice thing here is that when you take the derivative with respect to t of this constant, we'll just have 0 over 6, which is a concavity of 0, right? And that's not a function of t, it's just a constant value. So we can say here that we should be getting a 0 for our second derivative. The concavity is 0 because we can't even evaluate that. I mean, if you wanted to think about it this way, if we were to evaluate this at the t value of 4 that we were given, well, there is no t to plug in, right? So that is just going to maintain the same value of 0. And let's see what this is asking. It's saying, is this concave upward, concave downward, or neither? And so if we have 0, that is neither positive nor negative. So we cannot say it's concave up. We cannot say it's concave down. That's going to be neither. We'll submit our answers and we'll see what WebAssign tells us. Okay. Everything was good there except for our concavity. Not sure what they're looking for here then. Oh, so they're saying to put dne if our answer does not exist. Okay, so if our concavity, if our second derivative is 0, then we can say that there is no concavity, right? I think that's a better way of wording this, right? So I think that's what they're looking for here. It's always a good idea to go ahead and read those instructions, just to see exactly how they want us to frame our answer. But we got 0, which means it's neither concave up or down. So that means that the concavity does not exist. Okay. So we do have to just be mindful of those instructions, that the instructions that they give us there, the directions. If we get a 0 for that second derivative, then we're going to put dne for concavity. Okay. All right. There are some more complicated problems here, but it's really a paint by number situation. So I want to sort of switch gears and go to number 7 here, which is changing the question type to something that's a little bit more involved. This is finding the equation of a tangent line at a given point on the curve. So let's see what they give us here. They've given us our x and y parametric equations. So we need to find the equation of the tangent line at each of these points, and they've provided 3 different points for this curve. So remember, the equation of the tangent line should be a straight line. It should be y equals mx plus b, where the m represents the slope of that tangent line, and that slope is going to be our first derivative, dy dx, evaluated at some value of t. T equals whatever that value is going to end up being. It really depends on the x and the y values. So we'll have to use our x and y values to find out what that is, but I like to start off by just finding the derivative. So let's start off with the first part here. Dy dx is equal to dy dt over dx dt. And that one shouldn't be too bad. We've already done 2 examples. It kind of can get us going. So we know this is going to be a fraction. We might have to simplify it shortly, but we'll cross that bridge when we get there. So for dy dt, if we look at this function here, we should get 2t minus 2. Okay. And then for the denominator, if we're going to take the derivative of x with respect to t, that's going to be a 2t minus 0. So that's just a 2t. Okay. Now, if we want to do a little bit of extra simplification, I notice that the numerator here, both of those terms in the numerator have a factor of 2. So we could factor out a 2 from our numerator, which will leave us with a t minus 1, okay, over 2t. So that means that our 2's, our factors of 2, will cancel out. So our function that describes the slope of this curve at any given point is going to be the function t minus 1 over t, right? So now for each of these points, now that we have our derivative function, right, we need to find what t value generates these xy pairs. So I'm going to label each of these questions A, B, and C so that we can go through this systematically, kind of organize ourselves. So for A, we know that x is equal to 0, y is equal to 0. So we're at the origin, at least in terms of our rectangular coordinates, but we need to see what parameter t value we should get here. So we'll set our parametric equations equal to 0 and then solve those. So if I'm looking at the first one for x, we would have 0 is equal to t squared minus 4. And this is a factorable quadratic. So we have the difference of squares there. So that's going to be t plus 4 and t minus 4. Okay. I haven't been given any restrictions on the parameter t. So I know that at least for our x values, to get a 0 here, we can use a t value of -4 or +4. Okay. And just for good measure, I want to go ahead and check to see, can I do something similar over here for y equals 0? And do I have like some a kind of a t value that corresponds to these t values that I got over here. So we'll set this as 0 is equal to t squared minus 2t. Let's go ahead and factor that. We have a t in common, so I'm going to factor out a t. And then let's go ahead and say we have a t minus 2. Okay. So from there, we can say we would have, if we use the zero product property, we have t is equal to 0 or t is equal to positive 2, which do not match the t values that we have over here. So how can we say that we're going to have some sort of consistent value for t that will generate that point 0, comma 0? Let's think about this for a moment. Okay. Um, I took a moment to think about that, and what I'm noticing is that I factored incorrectly over here when I solved x equals 0. This is a difference of squares, which means these should have been 2's, right? Because 2 times 2 would be 4. So that was just an oversight on my part. So this should be positive 2 and negative 2 there. So that means that our solution for t were negative 2 and positive 2. And so we have this correspondence of the value 2 here. So what we want to do for part A is evaluate this derivative at the t value of 2. So what this will imply for us is that our derivative, dy dx, evaluated at t equals 2, should be 2 minus 1 over 2, which is just 1 over 2. So that should be our answer for this first slope, right? And what we can say is that the equation should be y equals mx plus b, and we now have m, right? Because this slope that we evaluated and found is 1/2, okay? So we should have 1 over 2 x plus, well, if you notice that this point that we're looking at is 0, comma 0, then the line tangent to this should have an intercept of 0 also, right? Because this is both an x and a y intercept, 0, comma 0, when we have a point at the origin. It is both an x and a y intercept. So our b value should just be 0. So I'm going to submit this answer and just check it, see if we got that. Boom. Okay. Great. All right, let me just toggle this a little bit. There we go. All right. So since we were able to find that out for A, we're going to go ahead and do a similar process for B and for C. Okay. So I'm going to erase some of this jazz that I have here. We're going to go through the same process, but we do want to keep the derivative that we found here. So let's go ahead and erase. Erase. There we go. Now we have a nice clean workspace. Let's switch our marker over to black, and we're going to look at part B. So now we're looking to evaluate the curve when x is equal to -3 and when y is equal to -1. So if we sort of plug these into our parametric equations, if we have -3 is equal to t squared minus 4, in order to solve this quadratic equation, we have to get it set equal to 0. So if I add this -3 over to the other side, we'll get 0 is equal to t squared, and then adding 3, we would get -1. This is another difference of squares, luckily. So 0 is equal to t plus 1 times t minus 1. So our t values that we're going to use here are either going to be -1 or +1. Okay. If we go ahead and plug -1 into the parametric equation for y. We get t squared minus 2t. And then if I add that, cancel out that -1, add it over to the other side, we should get 0 is equal to t squared minus 2t. And then we added the 1 over to the other side. And then we can ask ourselves, is this factorable? And this one is nice and easy to factor as well. It's not a difference of squares, but what we should get is a t minus 1 times a t minus 1, right? And since we have a repeated factor there, then we only have t is equal to +1 here. So since we have a +1 for both of these equations, we can go ahead and evaluate our function. So dy dx evaluated at t equals 1 is going to be equal to 1 minus 1 over 1, which is just going to be equal to 0 over 1, which you can just call 0. Okay. So that means that um, our slope m is equal to 0. Okay. So since our slope is equal to 0, that means that we have a constant function that describes the tangent line. And a constant function would be just a horizontal line that passes through the curve, tangent to the curve, and it just has that constant y value. So if we have a y value here, -1, that is the value that we need here. So I'm going to put y equals -1, and I'm going to go ahead and check that. Boom. We got that one correct as well. Okay. We just need to do this one more time. Um, and so let's do it yet again. Wonder if there's an easier way to erase all this stuff. Let me just take a moment to think about that. Let's find maybe my select tool. Yeah, there we go. Just delete all of that. There we go. And now we can go ahead and write part C in, which says x is equal to -3 and y is equal to +3. Okay, so we actually had done the math already for -3. So when we had -3 is equal to t squared minus 4, that's the exact same x value that we had before. So I'm just going to skip because we did have this as t needed to be equal to -1 or +1. You can go through that algebra again, move the 3 over to the other side, get that t squared minus 1, and then factor it. But since we did that before, I'm going to sort of cut some corners here. For this other function, the function y, we need to go ahead and work that out because we have a different y value. So 3 is equal to t squared minus 2t. We can go ahead and subtract 3 over to the other side of this equation, such that we now have 0 is equal to t squared minus 2t minus 3. And so we're looking for the factors of -3 that will add to give us -2. Well, the only factors of 3 are 1 and 3. And in order to get a -2, we need to have a -3. So this is going to factor into t minus 3 and t plus 1. So there, we're going to evaluate our derivative at t equals -1, since we have that correspondence for our parameter. Okay, so dy dx evaluated at t equals -1 is going to be equal to -1 minus 1 over -1. So that's going to be a -2 over -1, which is equal to -2. Okay, so that's my slope for this tangent line. So we can start the equation off by saying this is going to be y equals uh, negative 2x, okay? But we don't know what the value of b is, okay? So I'm going to switch some colors here. We know we have y equals negative 2x plus b. And in order to find um, the intercept of this particular linear equation that passes through the point negative 3 comma 3, then we can just simply plug the x and the y value into our linear equation to solve for b. So this would be 3 equals negative 2 times negative 3 plus b. So we get a positive 6, get a 3 over here, plus b. And if we want to isolate the b, we'll subtract the 6 over here. So we get these guys to cancel out. So b is equal to a negative 3, and that's going to finish up our equation. So this should be negative 2x minus 3. We're going to submit our answer. And not getting that right. Not sure why that's wrong. Let me go ahead and take a moment to think about that. Okay, I found the mistake after looking at some of the work that I did there. Some shoddy work on my part, but it happens to the best of us. Let's take a look at the when I evaluated the slope at this given point. So let's go ahead and bring out the red marker and punish myself. So real grade school mistake there. Negative divided by negative should have been a positive slope. That's positive 2. So when I went here with a negative 2 as my slope, that was incorrect, and it threw off my calculation of b. So let's go ahead and clean this up and start again with that positive 2 as our slope. Okay. So again, I have a colleague that he has this mantra in his classes that mistakes are expected, we respect them, we inspect them, and then we correct them. So it's all part of the process of learning. Nobody here is perfect, and those little mistakes are going to happen to you from time to time, especially when you're fatigued. So if you'll allow me a little bit of grace to correct this problem, I will do the same for you, I promise. So got that positive slope in this, so we need to put a 3 here for y, 2 times negative 3 for x, plus b, and the process will proceed as we intended. So this will be a negative 6 here. And in order to move that over to the other side of the equation, we'll add 6 to both sides. Cancel out the 6, and we get b is equal to 3 plus 6 is 9. So this should be 2x plus 9. And let's see if I haven't overlooked some other tiny little error. So positive 2x, and then this should be a plus 9. And let's go. Let's see if this works. Boom goes the dynamite. We got our 3 check marks. Okay. So the problems will get a little bit more difficult as you proceed, but finding those tangent lines is pretty much we'll follow along that process that we just went through. So I always think that it's easiest to write that slope intercept form y equals mx plus b just to guide you. I mean, at this point in your math career as top Calculus 2 students, you might sometimes feel that it's a little bit silly to write y equals mx plus b, but having those little reminders is always helpful. I mean, one really prime example is that I have not yet met a faculty member or a student in higher level math that does not repeat SOHCAHTOA to themselves when they are sort of processing trigonometric functions. So sometimes we just need a little bit of a reminder of those basic concepts because it's easy to overlook those little things. Okay, so we just want to get those reminders, go through that process, and hopefully these extra problems kind of help you out as you get through this homework assignment.